One might ask, how do we handle kinematics for rotating objects? When objects rotate, how do we quantify that? So to do that, we first define kinematics quantities for rotational motion. And I'm going to use the terms rotational and angular interchangeably. Like we defined a displacement and a position for regular motion, we are going to define a rotational displacement or an angular displacement for rotational motion. We use Greek letters as symbols for kinematic quantities for rotational motion. So the symbol for rotational displacement is the Greek letter theta. We define as well a rotational or angular velocity, and the symbol for that is the Greek letter omega. For acceleration, we define a rotational or angular acceleration, and the symbol for that is the Greek letter alpha. Okay, so these are quantities that we define for rotational motion that should be equivalent to the quantities we define for regular motion. For example, a rotational displacement. It can be something of the sort it made 10 rotations. That's a rotational displacement. Half a rotation is a rotational displacement. A quarter of a rotation is a rotational displacement. Or we can represent it, instead of saying rotations, we can use another unit. Degrees is 480 degrees displacement. 3625 degrees displacement. Or we can use another unit, and this is actually the SI unit, what we call radian, and we refer to it as just radian. Pi radians displacement. 24 radian displacement. For rotational velocity is going to be rotations per second, rotations per minute, rotations per hour, or degrees per minute, degrees per second, or degrees per hour. And for acceleration, it's going to be rotations per second squared, or radians per second squared, and so on. Now, once we define these quantities, we are going to use them exactly the same way we have used quantities for regular motion. For example, angular velocity, the average angular velocity between time ti and tf, we define it as the displacement during that time over the time. Theta sub I is the initial position, theta sub f is the final position, change in position, which is my displacement, over change in time. That's the way we define the angular velocity. The same way we have defined the regular velocity. For acceleration, change in velocity over time. Final velocity minus initial velocity over change in time. That's my angular acceleration. What if I have a constant acceleration? What would be the equation for the position? So if this is my acceleration, my constant acceleration, then my final position is my initial position plus 1/2 of alpha t squared plus the initial velocity times t. In other words, they are just the same equations we have used for linear motion. We just are using different symbols. To illustrate that, we look at them again. For linear motion, for example, final velocity is initial velocity plus at. For angular motion, final velocity is now in omega, is equal to initial velocity omega 0 plus alpha t, so we have alpha instead of a. Okay, we just replace the symbols. Now, for linear motion, position, for example, here we are using x. So in this case, we are going to use theta. So theta of t is equal to theta of 0, compare it to this, plus initial velocity times t, plus 1/2 of alpha t squared. Same, for constant acceleration, we have this equation. V squared is equal to V0 squared plus 2a x minus x0. Same equation. Omega squared is equal to omega 0 squared plus 2 alpha times the rotational displacement.